Condensation polymers are fairly common polymers that include things like polyesters and polyamides, such as nylon. We're going to take a look at how these things form. So for instance, here we're forming a polyester from an alcohol and an ester. It's a transesterification reaction. We're not going to look at all of the details of the mechanism, because hopefully that's familiar to you. But the alcohol functions as a nucleophile, and the oxygen lone pair will be donated to the carbonyl of the carboxyl group, opening up a pi bond to get to a tetrahedral intermediate. Now, the tetrahedral intermediate could just collapse. We could send those lone pair back again to push the alcohol back out. But if instead there are a couple of proton transfers to put the proton over on this methoxy group, then when the lone pair comes back down to reform the pi bond, it's the methanol that's pushed off as the leaving group. And so this is a condensation reaction because we're pushing off this small molecule as a leaving group. And if we continue this reaction over and over again, we're going to get a polymer, a polyester. So the important thing about polymerization in this case is that we've got nucleophilic substitution at a carboxyl, at an ester in this case. And the functionality of the monomers is too, meaning this alcohol has an alcohol on each end, and this ester has an ester on each end. And that means that each is capable of growing in two directions, linking together with other molecules on both sides. So eventually we get this alternating dialcohol, dicarboxylate, dialcohol, dicarboxylate polymer structure. There's another similar type of polymer, another way of making polyesters with a slightly different mechanism. That's to start with a ester that is only monofunctional, but it's a cyclic ester. It's in this case, a caprolactone. And these cyclic esters won't react on their own to make polymers. But if you add to them a Lewis acid, maybe, and an alcohol, then they start to react. And this is an example of a chain reaction. The Lewis acid plays a couple of roles here. It plays the role of approximation, bringing the ester and the alcohol together so they can react with each other. The alcohol, once again, is going to be a nucleophile. The ester is going to be the electrophile. And the metal also facilitates nucleophilic activation, because once the alcohol adds to the metal, it loses its proton much more easily. And so we can think of this now as an alkoxide, which is a much better nucleophile. And it's going to donate its electrons to this activated electrophile. That positive charge in the oxygen means it's a much better electrophile than before. And so we'll get this tetrahedral intermediate, and when it collapses again, I'm just going to swing this bond down here. We're going to push out either the alkoxide or less oxygen here. And if we push this oxygen out, we've opened up the ring. So now in this structure, we have the alcohol on the one end, and on the other end, we have the metal, and the metal's ready to bind another ester here and carry out the whole process over again. So in ring opening polymerization, we have a functionality of one. There's just one ester here, but there's an initiator that's going to start a chain reaction. It's going to open up that ester, and once it's opened up, that ester is going to become the new nucleophile at the far end, at the oxygen end, and it's going to keep reacting with additional monomers to form a polymer.